Welcome to The Explainer. Today we're going to take some actual Stanford-level computer science concepts and translate them into a completely relatable, highly visual journey. We're stripping away all that intimidating matrix calculus and looking right under the hood of artificial intelligence. If you've ever wondered what people really mean when they say they're training a model, well, you are in exactly the right place.
So let's dive right in by asking the most fundamental question behind all AI. How does a machine actually learn from data? When we say a machine learns, it's not sitting at a desk reading a textbook. It's executing a highly specific, repeatable mathematical process. We hear terms like algorithms and models tossed around every single day, but today we're going to look at the exact mechanics of that learning process step by step.
Here's our roadmap for the explainer today. First, predicting housing prices. Second, measuring our mistakes. Third, the gradient descent journey. Fourth, batch versus stochastic. And finally, the normal equation shortcut.
Section 1. Predicting housing prices.
Let's start with a really tangible problem. Instead of analyzing something wildly complicated, like, say, self-driving car data, imagine you simply want to estimate real estate prices. What we're talking about here is the essence of a supervised learning regression problem. It's an algorithm that takes an input, like the size of a house, and maps it to a correct output, like the price. It's arguably the simplest possible learning algorithm out there. It's called supervised because, well, we act as the supervisor. We give the algorithm the correct answers, the true prices of the houses, so it can actually learn that relationship between the inputs and the outputs.
And this brilliantly illustrates our starting point, using a real Craigslist dataset from Portland, Oregon. Fun fact from the Stanford lecture, this specific data was actually collected by the professor's father-in-law, who is just really into real estate. It's a pretty simple table. We've got our inputs, the square footage and the number of bedrooms, and our target output, the price. To build a learning algorithm, you absolutely have to start by feeding it a training set exactly like this one.
Now, the machine's entire job is to look at that data table and output what academics clunkily call a hypothesis. It's just the function outputted by the learning algorithm that estimates the price for any new house size. Simply put, it's just the rule or the formula the machine uses to make its predictions. You feed in the size of a brand new house the machine has literally never seen before, and the hypothesis spits out the estimated price. But how does it actually come up with a good rule?
Section 2. Measuring our mistakes.
Before a machine can get smart, it needs a way to realize exactly how dumb its current guesses are, right? We measure those mistakes using something called the cost function. This is a mathematical formula calculating the square difference between the algorithm's predicted price and the true asking price. Basically, the algorithm takes its predicted price, compares it to the actual price from our Portland dataset, squares the difference, and adds them all up. You can visualize this cost function as a massive 3D quadratic bowl. Any high point on the edge of that bowl, that represents a terrible prediction with high error. The absolute lowest elevation at the very bottom of the bowl represents zero mistakes, the perfect prediction. So the entire goal of machine learning is simply to get to the bottom of that bowl.
Section 3. The gradient descent journey.
The absolutely crucial point here is figuring out exactly how our algorithm navigates down to the bottom of that bowl. This introduces a foundational concept in all of AI, gradient descent. Imagine a blindfolded hiker standing randomly on the side of that massive hill. The math behind gradient descent is essentially that hiker feeling around with their feet for the steepest downhill slope. Once they find it, they take a tiny baby step in that direction. Then they stop, feel around again for the new steepest slope, and take another step. By repeating this loop over and over, the algorithm steadily walks down the error hill until it settles at the lowest possible point, the optimal prediction rule.
But this brings up a massive operational question. A student in the Stanford lecture actually asked this exact thing. How do you determine the learning rate? Meaning, how big of a baby step should our algorithm take? Think about it. If the step is too small, the algorithm takes absolutely forever to reach the bottom. But if the step is too big, the hiker might wildly overshoot the valley and end up even higher on the other side of the bowl. No way we want that.
With a bit of insider classroom charm, the professor notes that, quote, in practice, you set to 0.01. While there's a ton of complex theory behind it, in practice, if your data is scaled properly, you usually just start by setting your learning rate to 0.01. You test it out, see if the machine is successfully walking downhill, and you just adjust from there. It's a really great reminder that even the most complex computer science relies on practical, trial and error starting points.
Section 4. Batch versus stochastic.
Our Portland dataset was tiny, right? But what happens when our algorithm needs to learn from millions of examples, and computing every single step becomes overwhelmingly heavy? Here we pit two methods against each other. Batch gradient descent reads the entire dataset to take one perfect step. It perfectly reads the entire map, meaning it calculates the error across every single house in your dataset. It's a perfect, precise step. On the flip side, stochastic gradient descent is the shortcut. It takes a slightly noisy step using just one house at a time. Instead of reading the whole map, it looks at just one house, tries to fit that one house better, and takes a quick step. It wanders a bit noisily and randomly, but it moves incredibly fast.
To put this into perspective, imagine you're trying to predict housing prices using the entire United States Census database. We're talking 100 million examples. If you have 100 million rows, batch scanning is painfully, impossibly slow because it has to read 100 million rows just to take one single step. This is exactly why the slightly messy, zigzagging, stochastic shortcut is practically mandatory for modern big data. It never reaches the absolute, perfect global minimum, but it gets you close enough, much, much faster.
Section 5. The normal equation shortcut.
Finally, we reach the resolution of our journey. You might be wondering, is there a way to skip the hiker's tedious trek entirely? A way to bypass all those iterative steps and just land at the bottom of the bowl instantly? The answer is yes, but with a catch. The normal equation solves for the optimal parameters in one single mathematical step without any iterative hiking. For the specific case of linear regression, we have this magic teleportation spell. Through some incredibly clever matrix algebra, it solves for the optimal prediction rule instantly. You just plug your data in and boom, you're at the global minimum. However, as the source points out, this only works for basic linear regression. It completely falls apart for more complex algorithms.
So let's summarize our toolkit here. We optimize learning depending on the constraints of our data. If you have a small data set, use batch gradient descent for perfect accuracy. If you have massive modern data sets, use stochastic gradient descent for speed. And if you're strictly doing linear regression, you can use the normal equation to skip the line entirely.
As we wrap up this explainer, I want you to sit with this thought. If these foundational algorithms can perfectly predict a house price in Portland, how do these very same mechanics scale up to the massive neural networks powering today's AI? We just looked at finding the bottom of a mathematical bowl to predict real estate. But these simple steps, measuring errors with a cost function and walking downhill with gradient descent, they act as the literal building blocks for the most advanced artificial intelligence in the world. As you ponder the elegance of this system, ask yourself, how do these very same mechanics, layered thousands of times over, scale up to the massive neural networks writing code, generating art, and powering today's AI revolution? Thanks so much for learning with me today.